On this slide, the key message is simple. Teeny fines can cause huge furnaces problems. When we run a blast furnace, the gas must move smoothly up through a packed bed of coke, sinter, and pellet. For that, we need enough open space between the particles that we call void fraction or epsilon. The Ergun equation tells us that the pressure drop of gas through this bed is extremely sensitive to voids. As void spaces reduces, resistance doesn't increase linearly. It's increased in a very steep way, almost explosively. In this talk, we will see how a small amount of fines reduces void fraction, why that suddenly choke the gas, and how understanding this physics can help us avoid hanging, slipping, and unstable furnace operation. Here we focus on what void fraction actually mean for our furnaces. Void fraction epsilon is simply the fraction of the furnace volume. It is the fraction of the furnace volume that it occupied by gas, not by solid. More void means more space for gas to flow. It is simple. For typical blast furnace burden, epsilon in the shaft is roughly between 0.35 to 0.45 depending on the size distribution and packing. The Ergun equation shows that pressure drop delta P divided by the vertical height L, that is delta P by L, is inversely proportional to epsilon to the power 3, inversely proportional to epsilon to the power 3. This means if we can keep epsilon a little higher, say 0.42 instead of 0.36, the gas see much less resistance and the furnace breathes easily and comfortably. In practical terms, the high epsilon is a lifeline. It supports uniform gas flow, better gas utilization, a smooth, predictable descent of the burden without sudden sticking or slipping, and all these leads to reward the campaign life of the furnace. Now coming to our next slide, which is related uh, with the immense information. The equation contains the term like 1 minus epsilon bracket close to the power 2 divided by epsilon to the power 3. So epsilon appears in the denominator raised to the power of 3. When epsilon drops say 0.45 to 0.35, the pressure drop doesn't just increase by 20 or 30%. It can increase by 2 to 3 times under the same gas flow condition. This is the epsilon trap. To the eye, the bed looks almost the same, but aerodynamically, the furnace has moved into a very high resistance state. Operators can see sudden rise in shaft pressure, poor gas distribution, and increased risk of hanging and slipping for what looked like a small change in burden condition. The lesson is small decrease in void space are not small in their impact. The physics amplifies them dramatically, and Ergun equations qualify and quantify exactly how serious that amplification is. And many times it also open our eyes in this condition to have a good understanding of impact of even smaller fines in terms of pressurizing the furnace. On this slide, we connect epsilon to our choice of burden, especially pellet versus sinter. Iron ore pellet, when produced with a narrow size range and a good sphericity, tend to form a more regular open packing. This naturally gives a higher void fraction compared with sinter or lump ore that contain more irregular shape and more fines. A higher epsilon with the pellet reduces the presence of it, and there is a reduces the pressure drop also in the shaft and near the cohesive zone, so the gas can distribute more uniformly and reach the ore layer more effectively. In contrast, sinter or ore with a broad size distribution and fines tend to pack tighter, lowering packing void fraction, increasing delta P, and promoting zones with a poor gas flow. So when we design a burden mix, pellet are not just a metallurgical decision, they are also a gas flow tool. A certain fraction of pellet can be justified scientifically as a way to keep void fraction high and the furnace aerodynamic very healthy. Next we look at what happens when we inject very fine coal into these system. Pulverized coal injection send a cloud of fine particle into the raceway. Some coal burns, but some unburned or partially burned fines can lodge in the coke bed, effectively reducing the local void fraction around the tear zone. When we apply the Ergun type porous media model to this region, a relatively small effective reduction in void fraction due to accumulated fines can significantly, in a big way, increase the local pressure drop and disturb the distribution of a gas between different tier level and across the furnace cross section. Now the result is that what was designed as a coarse high void fraction coke bed can restart behaving more like a mixed fine coarse bed with much higher flow resistance than expected only from the coke size. Therefore, a stable PCI operation it not only about injection rate and combustion, it also depend on maintaining a good void edge by controlling coal fineness, combustion efficiency, and removal of fines from the coke matrix. Finally, we bring the discussion down to operator actions and routine. First, to keep epsilon high, we must be strict about screening and removing undersized burden material. Fine fraction quickly fill the voids between larger particles, sharply reducing void fraction and pushing the furnace towards the epsilon trap we saw earlier. Second, we should control the size distribution and layer thickness of the center pallet and coke so that bed should not pack too tightly and the void fraction remain reasonably uniform from the throat down to the cohesive zone. Third, our instrumentation, pressure drop trends, gas utilization indices and stock line descent pattern can be used as early warning indicators of deteriorating voidage. Any unusual rise in pressure for the same blast together with the irregular descent should trigger a check on fines and burden condition. The scientific message is clear. Treat epsilon as a controllable process parameter by consciously managing void fraction through screening, burden design, and PCI discipline. Operator can prevent many of the drastic instabilities before they ever appear in the furnace. So these are the operator action to secure high void fraction.